algorithm which finds the shortest path from a source to all other reachable vertices in a directed acyclic graph. So to start off with, we have this example of a directed acyclic graph, and I've written out some edge weights. In this case, we can use negative edge weights, and we're guaranteed to not have a negative cycle because it is an acyclic graph. The issue with a negative cycle is that it's hard to find the shortest distance from a source. For example, if we have this as a graph and it was a negative cycle, what is the shortest distance from the source to each of the vertices? You might say the shortest distance for A is -1 and for B is -1 minus 2, so that's -3. But that would not be the case as per our algorithm, because if you go along the cycle twice, the distance from S to A would actually decrease. Okay, so the distance between S and A would be -1, then I go along this path, so -2, then I go along this path, -3, then I come back here, so -1 again. So that's -7, which is less than -1. So technically this should have been the distance between S and A. So yeah, this is a very weird case. So we don't look at paths or graphs with negative cycles. Alright, so back to our problem. So we do have this directed graph, and we want to find the shortest path from the source, which I've considered to be A, to all other reachable vertices in the graph. Alright, so to begin with, we need to topologically sort the directed acyclic graph and record the order, because that's the order we shall be using for traversing the graph in the rest of the algorithm. So I'm going to perform a topological sort for this graph using the DFS post-order method. So we start off here. The pre-order visit time is 1. Then we go to this part because it has an edge distance of 1, which is smaller than 2. So this is 2, 3, 4, and we don't have anywhere else to go from here. So we record the post-order time. We go back up to the node that called it, back up again, and we come to A, but we haven't finished traversing through all of its children. So we go to B and record the pre-order time as 8, 9, and we stop pre-visiting nodes here. So we conclude that the post-order time here is 10. This is 11, and we end at 12. So the order of the topological sort, of course, we write it out in descending post-order times. So we start off with A, because the post-order time is 12. Then we go to B, then D, because the post-order time was 10. And then we have a post-order time of 7, which is the next largest post-order time. So we write C, then E, and finally F. Alright, so this is our DFS post-order method, topological sort times. And I did walk through this algorithm pretty quickly. I suggest going through what topological sort is if you don't know how to perform the algorithm or what the pseudocode of the actual algorithm actually is. Okay, so now we continue with the next step of the algorithm since we finished retrieving the topological sort order of the graph. So our next step is very similar to Dijkstra's. So we set initial distances for all the nodes from the source node. So I'm going to have an array known as dist and prev, just like I had in Dijkstra's. And the index number is going to correspond to the node number, where node A would correspond to an index of 0, node B would correspond to an index of 1, and so on and so forth. So we have 6 vertices in our graph. So I've drawn that out. And we start off by setting the initial distances to infinity for all vertices except for the source. And for the source itself, we'll be setting the distance to 0. Similarly for prev, we set all the values to null. Alright, now once we finish this step, which is really similar to what we did for Dijkstra's, we visit the vertices using the order from the topological sort, amending the prev and dist arrays to account for the shortest path. So I start off at node A, and since that has the shortest distance, technically, and we look at its children. If the distance from the source to the current child is smaller than the current distance recorded in the array, we amend the distance. So in this case, the distance 1 is smaller than the distance 0 plus infinity, which is infinity. So we amend this infinity value to 1 for C, and for B, we amend the value to 2. We also update the prev array and set the prev values for B and C to A, since A is the node that changed the distance values for B and C. So we finished going through A, and now we go through B, since that's the next node in the topological sort order. As we go through B, we notice it has just one child, which is D, and the distance from the source to D is currently recorded as infinity, and the current distance that we're noting right now is the distance from A to B, which is 2, plus the distance from B to D, which is -4. So 2 minus 4 is -2, and -2 is smaller than infinity, so we change this value to -2. Next, we also set the prev value for D to B, since B is the node that changed the value of D. We finished going to node B, and now we go to node D, since that's the next node in the topological sort order. And since the distance from A to D is noted down as -2, and -2 plus 4 is 2, which is smaller than infinity, which is the distance from A to F, which is recorded in the array, we change this value to -2 plus 4, which is 2. And we also set prev to D. So now we go through C, and we look at the children for C. The only child of C is E, and the distance from A to E, currently recorded in the graph, is infinity, which is greater than the distance from A to C plus C to E, which is 1 plus 1. So that's 2. So we change this distance to 2 and set null to C. After we go through C, we come to node E, and for node E, it has just one child, which is F. The distance from A to E is currently recorded as 2, and the distance from E to F is 2. That sums up to 4. However, 4 is not smaller than the current distance recorded from A to F, which is 2. So we do not change anything in the dist or prev arrays. Next, we come to F, but F has no children, so we can terminate our algorithm here. So what is the shortest path from the node A to all of the reachable nodes in the directed acyclic graph? So we look at our distance array, and we have these distances which correspond to the distance from node A to each of the other vertices in the graph. So for example, this is the shortest distance from node A to node D. And if we say the shortest distance is -2, so 2 minus 4 is -2, and this is the shortest path from A to D. We note down the prev array for the sake of knowing
the node along which
we travel in order to get the shortest path. So in the example for node D, we noted down B as the prev node, which meant that our path was from node B and not from any other node. In the case of F, similarly, we have the shortest distance recorded as 2, which is the case when you pass through node D. So from this path, and we know for node D, the shortest path was from B, so it was through here. For node B, the shortest path was from A, which is through here. So this is the shortest path for node F, and the distance is 2.
Here's a quick note on the pseudocode for the algorithm as well as the runtime. So this is the pseudocode. I recommend walking through it. And the runtime for the algorithm is linear. In particular, the runtime is O of V plus E, where V represents the number of vertices and E is the number of edges. And I've analyzed it over here. It's pretty easy to go through. Okay, so that's the algorithm for the shortest path from the source to all reachable vertices in a directed acyclic graph. Hope this helps.